Now in the last lecture we talked about elements, or different versions of atoms. And we talked about how you put them in a periodic table that indicates that they have different physical and chemical characteristics. Elements are basically the smallest unit of matter that cannot be broken down chemically any further. In other words, it's the smallest example of one kind of atom. You can physically break down the elements or atoms into smaller constituent parts, but you cannot chemically break it down into smaller constituent parts. It is the smallest unit of matter that has its own chemical and physical properties, and as such, if you cannot chemically break down an element any further. Now, the elements will also be an example of an atom, a different type of atom, which depends on how big the atom is, basically, or how many things are in it. And we represent these elements using symbols. We talked about all of this in the last lecture series. And we also talked about how they're made of protons, neutrons, and electrons. Now, who had this idea of the atom? Because we certainly shouldn't be able to see it, right? Well, first of all, the idea came up with a guy called Democritus. He was a philosopher from the Greek era, so this is like 300 years before the Common Era. And he basically came up with the idea by looking at a beach. And he saw how the beach looked like this one solid structure, but if you look at it closely, it was actually made of tiny little grains of sand. And he said, well, maybe the universe is like that. Maybe we're living in a universe that's made of these tiny, small building blocks. And he was absolutely right. The universe is made of energy, and sometimes energy is trapped in a space-time to actually become tangible, and we recognize that as matter. Now, what is the size of the atom? You certainly couldn't be able to see it, right? Atoms are really, really small. Well, if in terms of scale, this is the human here, and the human would be about between 1 and 2 meters tall, and you get smaller than that, you get muscles, smaller than that, you get tissues, smaller than that, you get, things like cells, smaller than that, you will get things like prokaryotic cells. Keep going smaller, you can get things like viruses. Keep going smaller, you get things like organelles. Keep going smaller, you have macromolecules like proteins and lipids and DNA. Go smaller, you get smaller molecules, which make those molecules, which call them monomers. Go smaller, you have simple compounds. Go smaller, you have the atom. The atom is about 0.1 nanometers across. That's even a new unit that was invented because of that. The atom is so small that they had to invent a new unit just to measure it. We call it the angstrom. It was invented by a scientist to actually measure the wavelength of light. And that's as small as it gets, pretty much. The size of an atom. Atoms are tiny, tiny, microscopic things. And if you were to shrink atoms together, just to put in perspective, you have billions of cells inside of you. And each one of those cells has billions of molecules inside of them. And each one of those molecules is built, some of them, by hundreds of atoms. And each one of those atoms is built by subparticles. But if you count the atoms inside of you, it will be an unsurmountable number. You couldn't imagine that number of how many atoms you have. And so that just comes to show that atoms are very, very tall. Now, different atoms will actually have different sizes, because it will depend on how much stuff is in it. Some atoms are bigger than others, and we'll talk about that in a second. But you certainly shouldn't be able to see one, right? Well, actually, you can see an atom. Now, this is brand new science. This is less than 10 years old, but we invented a machine that can take a picture, well, not exactly, but it can kind of take a picture of an atom. What you see here is the first detailed images of atoms in various arrangements. What you're actually seeing is the electron cloud of the atom. How on earth did they take that picture? Well, it's not really what you think of as a picture. Basically, they get a laser and they shoot at the source. And then that laser will bounce, so this is a close-up here on the bottom right, will bounce back on the surface and kind of push the surface down. Remember, light can act like a particle. So this laser, light acting like a particle, will push into the surface, which will then be dipped into whatever is trying to actually scan. So the actual sample stage is below that. And you see how the tip will actually move inwards into the surface as the laser is hitting it. Now, the laser reflects off the surface and goes back to a photodetector that detects the light of the laser. Now, if the laser is shaking, it can tell you that it's going through a surface that's going up and down. And since that is tiny little fluctuations can be measured, because you're going to be measuring basically tiny little changes in the wavelength of the laser. So you can measure things as small as you can measure the wavelength of the laser. And we're pretty good at doing that because it will change the color of the laser, and we can pretty good at detecting tiny color fluctuations. And so doing that process, we can actually scan an atom. This machine, by the way, is called the atom force microscope, and appropriately so, since it can actually scan the atoms. And that's pretty freaking crazy. So when I went to school, we used to say you can never see an atom. It's theoretically impossible. There's many reasons for it. It's so small that even if you try to see it, you wouldn't ever be able to see it. And they also said things like, you know, you're going to shine a light on it, and the moment you shine a light on it, it's going to hit it with full of energy, which will make that atom jump somewhere else, and then you can't see it. You can never focus use a mirror to focus the light that's that small. But see, we got away from that by using this procedure. We don't have to focus the light in this case. We just use slightly little changes in the wavelength of the laser. And this is amazing science that just comes to show you. When I went to school, they said it was impossible to measure an atom, and here we go. Atoms have been actually measured. Now, this is far from actually a picture that looks like the models that you see in these drawings that you see in this presentation, but it's an atom. You actually see the electron cloud, and that's pretty amazing. But it's still very, very small. Now, atoms will be basically built of two basic parts. It will have what we call the electron cloud, which is going to be on the outside of the atom. And then it's going to have the nucleus on the inside of the atom. Now, when you actually look at that, you soon realize that the atom is actually made mostly of the electron cloud. Most of the space of the atom is taken up by the electron cloud. So the electron cloud takes most of the volume of the atom. But the electrons are leptons, which are so tiny and so minuscule in mass that they basically do not count. Most of the mass of the atom is in the nucleus, which is made of protons and neutrons built of 3 quarks each, which means they are hadrons, or compositive particles made of smaller quarks. In this case, a special type of hadron that's in the nucleus of atoms, which we call nucleons, which are basically the protons or neutrons. But since each quark is hundreds of times bigger than an electron, so you're talking about a proton in the order of 1840, so 1840 times the mass of an electron, which is why when we calculate the mass of the atom, we ignore the electrons because it's so little. Okay? Now, the electron cloud, being on the outside and being made of electrons, will be negatively. So the cloud itself is negatively charged. So the majority of the space of the atom is negatively charged. But an equal positive charge will be in the nucleus of a stable atom, or a normal atom. And it's because of the protons which are there. Now the neutrons don't have charge. This means that atoms have a neutral charge, where the same number of protons and electrons will cause the overall charge of the atom to be 0 if it's on a stable natural state. So that's basically how the atoms look like and the different particles that make it. So you have the electrons negatively charged on the outside, and you have protons and neutrons in the nucleus. Now you may be asking yourself, why are there neutrons in the nucleus? What's the deal with that particle? Now, in fact, there are some atoms that do not have neutrons. The simplest atom there is, the hydrogen atom, does not have a neutron. It's just basically one proton surrounded by a tiny little electron. That's it. That's the simplest atom, and 99% of the matter on the Earth, on the universe, is going to be like that. And that's what the stuff that stars are made of, until they actually get this stuff and fuse it into bigger things. So all the elements you see on the universe are built on stars, either doing their lives or doing their massive explosive destruction that happens in some stars. We talked about that in the beginning of the year. All these elements, the naturally occurring ones, are created in stars. The very massive stars go all the way to iron. They build iron. And the ones which are less massive will build things which are less massive than that. Some build all the way to carbon. Something like the sun will build some beryllium, some like small atoms, but nothing huge. And basically every star builds at least helium out of hydrogen. But elements are built inside of stars, which basically fuse them as they force them to go towards each other and collide with each other and make bigger and bigger elements. And we do the same thing to create elements ourselves. All the human-made elements in the periodic table are made by forcing smaller atoms to collide with bigger atoms. Either way, the atoms normally have a neutron, though. As long as you have 2 protons, you're going to need a neutron. And that's the deal with that. Because basically, the protons have positive charges, which means by electromagnetism, they're going to be exchanging photons between the 2 of them here. And this is going to be causing a repulsion force in this case. All right? And if it was positive and negative, you cause an attraction force, which is actually what holds the atom together, because the electrons are attracted to the protons, which are inside the nucleus, like we talked about in the beginning of this video. But the protons will actually repel each other. Now, if you have a lot of these protons all sitting in the same spot in the nucleus, you have yourself a problem. This nucleus is not going to stick together, and there's no way you can make an atom like that. Even though you have the residual strong force, which we talked about in the quantum lecture series, holding the nucleus together, it won't be enough to hold the nucleus together. So the only thing you can possibly do then is actually have a particle in between that, which we call the neutron. And these neutrons will actually isolate the protons from each other so they don't have to touch. And that makes it easier then for the strong force to go around and hold it all together and hold the nucleus of the atom together. So it's the strong force that holds the nucleus of the atom together, and it's the electromagnetic force that holds the atom together, attracting the electrons to the protons during the nucleus. And the only reason they fall into the nucleus is because they're spinning very fast, and inertia throws them outside and balances out the electromagnetic force, the centrifugal force, basically because of the momentum of the electron. They're spinning in circles, and so the faster this electron spins, the more outward it would actually move. And that's important later on in lecture series. Now, I also would like to remind you that atoms are actually built of smaller particles either. Electrons are not made of anything. They are fundamental. There's nothing smaller that we know of. But the protons and neutrons are actually made of smaller things even. The neutrons have 2 down quarks and 1 up quark. Now each down quark has a 1/3 of a negative charge. So you have 2 of those, you get negative 2/3. But each up quark has a positive 2/3 of a charge. So that's 2/3 negative plus 2/3 positive. So the neutron has no overall charge. Now the protons would actually have a charge because they have 2 up quarks and 1 down quark. Now up quarks, like I said, have 2/3 of a positive charge. If you have 2 of those, you have 4/3 total. But then you have a down quark there too. So you have 3/3 total, and that's 1. So that's why protons will have a total of 1. So the protons will have a positive charge, and the neutrons will have absolutely no charge. They'll be neutral, and they'll be serving to separate the protons in the nucleus, allowing the nucleus to actually stay together. Now you have the strong force holding each one of those protons and neutrons together, or in other words, putting the quarks together, and then you have the residual strong force holding the whole nucleus of the atom together. And then you have the electromagnetic force holding the atom together. So, even though you may have not seen the lecture series, remember that protons and neutrons are made of smaller particles called quarks, and then there's also particles like the electrons, which are called leptons, and the other example are neutrinos, and both of those are called fermions, the basic building blocks of matter, quarks and leptons. The atom has examples of both. Electrons are lepton, the quarks are the other kinds of fermions. There's also bosons, and bosons are the particles which mediate the existence of the forces which permeate nature. Using particle accelerators, we actually made atoms collide with each other, made protons collide with each other. And we spat these atoms towards each other and actually made them collide. The way it works is you basically have an electromagnetic field to push away all the protons in the middle here. So you basically make a negatively charged outside, which pushes the protons in the middle. Then you use another field to propel the protons down the circle of the accelerator. Keep spinning faster and faster and faster through these tubes that you see down here until it finally reaches really close to the speed of light. And when you get that, then you make it collide with the target, usually a stationary or another moving proton that's going against it. And then that creates an explosion of matter that looks kind of like that, which can be scanned by a computer, and you can learn about the fundamental particles of matter. And that's how we found out about fermions and bosons, the basic things which make stuff and make stuff do stuff. Fermions, like quarks and leptons, actually are the things are made of. Bosons are the things that make the things do things. And so I would think of it as 2 aspects of the same reality. Fermions are the things are made of. Bosons are things that make things do things. So fermions is what is, and the boson is what does. But they're both aspects of the same energy, which is what the universe is made of. The universe is made of energy. And they're all basic different types of energy trapped to make a job. In the case of fermions, become matter. In the case of bosons, to create forces. Now, just to give you a taste of what's out there and what we're researching, in particle accelerators, we've been looking for the elusive tachyon particle, which is the particles that can actually move beyond the speed of light, beyond the speed of the photons are going at, the speed that other things which have mass can not only dream to get at. And if we can find this particle, it will have implications for things like time travel and other things like that. And very recently, we actually found possible evidence for a neutrino that did just that. And if you want to learn more about that, watch the video lecture series on quantum physics, where I will go into this on more detail. Alright, see you in the next video.